We're going to continue on with lesson 2.2 regarding inductive and deductive reasoning. We took a brief examination into some inductive reasoning by pattern is what that is. So we were taking a look at this equation in the previous lesson, which is when we discussed Carl Gauss and the figurate numbers, right, and how to do a summation. And this is what's known as the recursive equation. Recursion is going to depend on the result of a previous term, which is similar to patterning, right, where we need the results of some other previous piece of information in order to make a conclusion. So that's what we're going to work with inductive reasoning. And say that what that is it's reasoning through previous knowledge, which is also just experience. It's knowledge that you're going to empirically encounter. So to give you two of my favorite examples, and I've used this this example to teach this for many years regarding the difference between inductive and what we're later deal with deductive reasoning. So the first thing is the first crow I saw was black. The second crow I saw was black. All of the crows that I've ever seen are black. Therefore, all crows are black. Now, it's not that outrageous of a conclusion to make, because I would surmise that nearly all of you, I would even say every single student I have ever had, has only seen black crows, and that we are fine with saying that all crows are black based upon that we have not had a counterexample to that particular statement. So something just to consider is that whether or not this is true, based upon our reasoning being from what we've experienced that all crows are black. Commonly, I get the assertion. One, students bring up that they could change the color of the crow, like they could dye it a different color or paint it a different color. It's a barbaric suggestion, of course, but that's not what we're discussing here. We're just talking about the natural pigmentation of the feathering of the crows, right? Because then there's people who say, oh yeah, of course, if you remove the feathers, there's a different color in the skin, and that's not at all what we're after. We're just talking about we see a crow, what color are its feathers, and it's black. I also at this juncture usually get someone brings up that there are albino crows, except for that. Usually they've never seen one. They just know that albinos, the mutation of being an albino genetically is something that happens in other species. So therefore it could happen within crows. I mean, if you've been to the zoo, you've seen albinos potentially. May have even seen an albino human being. It's exceptionally rare, but it is something that exists. Again, something though that I have not met somebody who's experienced, having seen an albino crow. So it's not unreasonable, but there is a bit of a shadow of doubt as to whether or not it's true based upon this reasoning. So what we're going to examine and what we're going to try to transform our thinking in this course mathematically is through deductive reasoning, which is reasoning that uses facts, previous definitions, or premises to draw conclusions. So let's construct a similar thing with deductive reasoning. All crows are black. I saw a crow. Therefore, it is black. Notice that we define what crows by being black, whether that's true or not. But when we have that counterexample, it's going to just say that in order to be a crow, it must be black, and it makes the conclusion a lot cleaner to come to. Think about what Gauss had, with the recursive equation. There's a way to actually do this. Remember that we took the sum of the first 10 numbers, right? So trying to think of a way to complete the same problem, not relying on what we've previously experienced. Because one of the things that you come to with inductive reasoning is, what if you have no frame of reference? What if there's no experience, right? How do we sum up the first 10 numbers if we don't even, we don't have a single number to start with, right? We in order to sum of the first 10 numbers, we have to take a sum of the first 9 and the first 8 and the first 7, right? In order to add on one more each time. So what we can do instead is the following. There's an equation. So we're going to take those number of numbers, right? And we're adding first and second, first and last, and then, after that, right? For 10, it was 10 and 1, and 9 and 2, and 3 and 8, and so forth. So we were pairing everything up. So we took the number of numbers, 10, and we paired them. And there were 5 total pairs, correct? And then there was the sum, which we added, of course, that last number with the first one. And when we took the product of those two things together, it gave us the answer, which was, in the case of the first 10 numbers, was 55. Now check this out. So this is going to be n squared plus n over 2 is another way we could actually write this, right? If you were to distribute that n over 2 into the quantity n plus 1. This, mathematically, is what's referred to as the explicit equation. It doesn't require us to have any previous knowledge of other terms. We can actually just take that last number and push it through this equation, and then have an outcome and have a clean conclusion from there. Next, we're going to discuss more forms of deductive reasoning, which we're first going to take a look at the law of detachment. Make sure you spell detachment properly here. Well, the law of detachment says as the following. It says that if A, then B, A is true, therefore B. Now, some of you might be looking at these 3 dots. This means therefore. So it's, again, some of this beloved notation that we have mathematically that keeps us from having to write entire words. The idea being that if you pass the final, then you pass the class. Statement A is you pass the final, that occurs, right? Therefore, you pass the class, okay? So you have a condition, the first condition is satisfied, therefore the second condition is satisfied. That's the law of detachment. Next, you will recognize this, I hope, from when we discussed properties, and this is the law of syllogism. The law of syllogism takes 2 premises to make the conclusion. There are 3 subjects, each used twice. So it works like this. There's a famous syllogism that we get from Aristotle, and he was kind of the godfather, if you will, of syllogisms. He's recognized as the first one to construct one of these. So we'll take all men are mortal. Socrates was a man. Therefore, Socrates was mortal. Okay, so we have our three subjects, right? Men, mortal, and Socrates. And then men is used twice, right? Men, man, doesn't matter if it's plural or not. Mortal and mortal, and then Socrates and Socrates. 3 subjects, each used twice. Okay, there's this notion of that there's the major premise and minor premise. I'm not so concerned if you have knowledge of that, but what you'll notice is that this is effectively the same as the transitive property, right? Where we're going to take, we're going to equate these, Socrates with being mortal because these previous 2 terms were already set. If A is equal to B and B is equal to C, then A is equal to C. In this case, if A is equal to B and C is equal to A, then C is equal to B, right? So that is that. So if you have any questions, please feel free to contact me. And your assignment for the second part of lesson 2.2 is on Canvas.